and mathematical equation we have seen. So other things they are giving what are the different how to calculate this short noise for different currents. So 1.6 milliamperes current, if you are generating 1.6 milliamp current is going to flow inside the device, and you are going to have a barrier which is going to be crossed in 1 femtosecond, then they can say we can neglect the effect of short noise. The potential barrier is very, very small, then the short noise will become insignificant. But the potential barrier is very big and electrons need more energy to cross the potential barrier, then this short noise will become significant. Okay, so this short noise will become significant. So the no short noise, initially when the thermal noise was invented, this short noise was not that much famous because it is present only in selected devices, not present in all devices, right? And this short noise also not as dominating as your thermal noise. So the short noise was not given so much importance, but it is also going to have a noise power generated, which is going to be evident in all the amplifiers. So if you want to physically hear how short noise will be, you take an audio system and you give a very low DC current, and you hear the sound coming out of the amplifier using a headphone. You can see that if you throw a stone on the wall, you can hear distinct sound of each stone, right? So that sort of sounds can be heard from the amplifier if you are going to give a very small current to your audio amplifier. So that is how physically you can hear short noise which is coming out of a amplifier circuitry.